Hey, this is Dr. B, and let's talk a little bit about alkanes. These are just garden variety hydrocarbons with a general formula of CnH2n plus 2. You might think of them as a bunch of CH2 groups or maybe branched ones with an extra hydrogen at the tips, rendering it CnH2n plus 2, CH4, C2H6, C3H8, etc. No double bonds, so they are considered to be saturated. If they had double bonds or even multiple bonds, we'd call them unsaturated. And since they only contain carbon and hydrogen, they are hydrocarbons. They're very greasy. They're very nonpolar. This is because both the carbon-carbon bond and the carbon-hydrogen bond have similar electronegativities, and therefore they are nonpolar bonds leading to nonpolar, think greasy, substances. You could say hydrophobic. This means two things. It means they're going to have relatively low boiling points. They can't do much in terms of intermolecular forces, right? It's going to be dispersion forces only. And it also means that they're fairly inert. There's no obvious points for nucleophilic attack. That means a lot of the plastics derived from alkenes, but having alkane types repeating structure, they will be pretty unreactive, right? They are pretty good for storing just about anything. And so there's no obvious site for nucleophilic attack, but we better say what the word nucleophile means in case you haven't heard it before. By definition, it means nucleus loving, which is kind of the opposite of what it is. That's what it's attracted to. Therefore, it's electron rich. So it doesn't have or doesn't necessarily have a formal negative charge, but it's at least partially negatively charged, partially electron rich. An electrophile would be the opposite. That means electron loving. So an electrophile, think of something with a little positive charge, a little bit electron poor. This is a very important part of organic chemistry since it shows you where chemical reactions will probably occur. It gives you a mechanistic insight into how organic substances behave, and that's important because there'll be almost too many things to memorize if you're taking a full-on organic course, so a mechanistic approach is the way to go. And a way of simplifying it is to think that, hey, ionic compounds are formally positive and negative. It's pretty obvious what's attracted to what. Organic chemistry is really no different, but you have to deal with partial positive and negative charges rather than formal ones. Okay, one thing alkanes I'm sure do is burn. So let's burn some hexane. That's C6H14. I'd like you to draw it out and write the complete balanced chemical equation with the coefficients. And if you did that, and I hope you did, you should get this hexane combines with oxygen to make carbon dioxide and water in a 2 to 19 to 12 to 14 ratio. I think I'll take the trouble of making sure we can balance that out. And notice that the hexane is probably in a liquid form. Oxygen is certainly going to be in a gaseous form. It'll make some gaseous carbon dioxide, and typically it's so hot that the water is also as a gas. So those are the phases. If we start with 6 carbons, we better end with 6 carbons. So I'd originally put a 6 there. If we start with 14 hydrogens, we better end with 14 hydrogens. I'd put a 7 there. And then we would just have to work out oxygen. Here's the strategy, and this messes up people a lot. If you know the total number of oxygens at that point, and that would be 12 plus 7, 19. Remember, our original numbers here are just 6 and 7. That means we need to account for those 19 oxygens. So I just write a 9.5 there. Why do we have 19? Well, there is no such thing as half an oxygen molecule, so IB chemistry and perhaps college chemistry don't really care if you use half a molecule, but other people like to use whole numbers, so you double everything, 2 to 19 to 12 to 14. This is a kind of chemical reaction that might be bad for the planet, since carbon dioxide is responsible for global warming. Now, what do they do in terms of chemistry besides burn? Well, like we said, they're not particularly reactive, but if you hit them with a halogen, meaning like, say, chlorine gas, and some UV light, we can make some haloalkanes. So that would just be substituting a hydrogen for a chlorine or a bromine or an iodine or a fluorine, so they can halogenate, and that can then give you a handle to do other things with them. But the reaction is pretty extreme. What you do is you generate free radicals. Now, this may be your first introduction to seeing these sort of arrows that show the detailed steps of a chemical reaction. So I'm going to take a minute and just go ahead and explain some detail. This is a rare case where we're going to use single-headed arrows because we're dealing with a one electron process. So if you see a single arrow going onto there and the other one onto there, they're saying, well, hey, a bond is 2 electrons, let's split it in half. They call this homolytic cleavage. This is very rare. Almost all electron processes are more 2 electron processes, but UV light can generate these free radicals, and they're implicated in all sorts of nasty things. But once that thing is formed, it is going to do something. It desperately wants that other electron. And what it will do is it will react with just whatever's nearby. It can rip off the hydrogen free radical and generate a methyl free radical. That methyl free radical can react with bromine again to generate another bromine free radical, and now it's off to the races again, and then it could propagate some more. Eventually something will happen to stick them back together. So if 2 of those radicals then recombine, you've got termination. I hope you're seeing that there's about 80 different types of substances which can form if this thing happens, right? Well, I don't know about 80, but there's a lot of different substances that can form, and probably a lot of them do. So it's a fairly uncontrolled sort of chemical reaction. But hey, you can use it to make halo alkanes. One way to check for the reaction that's pretty old-fashioned and straightforward is if you've ever worked with bromine gas, it's an ugly brown liquid, I should say, at room temperature, but it's a fuming, nasty gook. Anyhow. So that when you start the reaction, clearly it's going to be messy and brown. But when you're done, if all the bromine is consumed, it will be colorless because no more bromine there, so you can check it to see if it's turned colorless. Okay, so what we've said is that alkanes can burn to make carbon dioxide and water, or they can halogenate using halogens and UV light, and a little bit about mechanisms, particularly these single electron, one-headed arrow processes. This is an introduction to alkenes.